We're now going to talk about Java monitor object synchronized statements. This is a contrast with the synchronized methods we talked about before. And so this will give us a chance to provide synchronization without using the synchronized keyword in the method declaration. And it also gives us a chance to get finer granularity of locking if we need that. So as we saw when we talked about synchronized methods, there are several constraints that they incur or embody. One is this issue of excessive coarse-grained serialization. So synchronization occurs at the method level, not at a finer level of granularity within the method body itself. And it also synchronizes on the one and only implicit lock, in other words, the this object, which can very easily become a source of contention, as we have seen here. So an alternative way to do this is to use synchronized statements. And to make this clear, we're going to take a look at a class that's implemented in Java, in the Java class library called the exchanger. And this defines a synchronization point where threads can pair up and swap elements within pairs. Not entirely sure why you'd ever want to do this, but it's in Java, so I figured I'd use it, and it's a great example of the concept of the difference between synchronized statements and synchronized methods. So here's an implementation, which is actually not the one you get out of the box in Java, because of course the people who did this were smarter than that. But just for illustrative purposes, here's an implementation where we have a synchronized method called createSlot. And this is coarse-grained. You'll see what I mean by that in a second. So what createSlot is going to do is it's going to come in with an index, and it's going to make a new slot object. And then it's going to say, is the index in the array A, here's the array. This is an array of slots, which has a bunch of slots, a capacity number of them. It says if the index of A sub index, or sorry, if the value of A sub index is null, we're going to go ahead and assign that location in the array to a new slot that we just allocated here. That's what it's doing. So the problem here is that this will be synchronized for the entirety of this particular method, but we don't need it to be synchronized for the entirety of that method. We only have to have it synchronized when we're going to go and check something and update it. This, by the way, this is also lazily creating the slot if it's the first time it's accessed. So here's another approach where we limit the scope at which the lock is held. Same lock, it's just the scope is limited. This scope was the entirety of that method, whereas down here, we only synchronize the part where it matters. And the reason why that is, if you take a look up here, calling new slot, that does not need to be synchronized. There's no need to do that because it's not an issue. It's not going to be shared mutable state. So in this particular case, we're only going to lock when we absolutely need to. So this demonstrates the use of a synchronized statement to give you a finer level of granularity of the scope over which the lock is held. Now, is this a big deal for this example? Probably not. I mean, we're talking about nanoseconds of overhead, but if you can imagine a more complicated example, then it would matter. So we allocate the slot outside of the synchronization region so that that is only locked for a very, very, very short period of time. And in this particular case, we're using this, which is the intrinsic lock that's used to serialize access. You could also use an explicit lock. So this uses the implicit lock. This uses this. But there's nothing to stop us from using this as the synchronizer. In fact, that actually might be better because if we do this way, then we run into that problem I talked about before, where if another thread comes along and synchronizes on the instance of exchanger, this thing will also be locked as well. Whereas if we do it this way with some explicit lock that's based on state here, then if you go ahead and synchronize on an instance of exchanger, that will not affect this synchronized scope. Ridiculously subtle, but not a bad thing to keep in mind. And this is useful when the intrinsic lock is too limited or too contended for some other reasons. So let's talk about the pros and cons of synchronized statements. So one of the pros is it allows you to use a private field. So that problem we talked about before, where somebody synchronizes on an instance of an exchanger, that will not affect other threads that are accessing the exchanger, because that's not using this, it's using some private field in this case. Oh, and of course, the other reason is that it gives you fine-grain synchronization, right? That's the other pro. I don't know why I didn't have that listed there, but that's really the main pro of synchronized statements, is that it allows you to have finer level of granularity of access by multiple threads. I'll have to add that too. That was dumb. There are some downsides. The syntax is more complicated. It's not the end of the world. It just, you have extra stuff in here. This is maybe arguably a little easier to understand than that. I don't think it's all that hard in practice, but it could be harder. And what I'm going to do now is talk about something called the double-checked locking pattern. And what's interesting is that this code that we see here, which is actually the code that comes out of the box from the Java class library, implements something called the double-checked locking pattern, which is something that you can read about here. And I documented this pattern about 25 years ago. It appears in my book, and I'll give you a link to the paper as well. I think you can get the paper if you go to this link. There's a lot of interesting stuff going on in this discussion. What happens with the double-checked locking pattern is that synchronization is done lazily when initialization is first performed. And as you can see here, the way this works is what we're having here is, this is a method called doExchange, and you can see it comes in and it says, if the slot is null, then lazily create the slot. So we go in here, we say arena index, get the slot. If the slot is null, then we lazily are going to initialize it. And this is the double check locking. We first check to see if it's null, and only if it's null do we go ahead and acquire the lock. If it's not null, we don't acquire the lock. So that's basically the gist of the double checked locking optimization pattern. And this all works because of some semantics in Java. If you really have a hard time falling asleep sometime, go ahead and take a look at this link, because it talks about how reads and writes to references are atomic in Java. So that's why we don't have to do any locking here. And we only create a slot if the slot is not currently created. And we only synchronize when the slot is first created. So that's the other part of the double-checked locking pattern. It does not require locking except when you actually have to initialize something. If you really want to amuse yourself, you should take a look at this link, because this particular pattern generated a firestorm of controversy that raged for years. Mercifully, the people who did Java, especially my friend Doug Lee, eventually realized it was actually a good thing to have support for, so they added that support in Java, and you can read about it here and other places. But it's interesting to see the history of the discussions of this particular pattern.